John is going to videotape because I intend to be a showman now, but we thought maybe I should use self and others. I think he was offering to borrow the tapes in case you forget.
Send me a mail or tell me in class, and I'll bring the tape of whatever lecture next class, and then give it back to me the following class.
I intend to watch them myself to make sure that I don't have any obnoxious habits. Okay, I think we finished reader's writer's problem, correct? And the next chapter I just want to kind of very, very quickly breeze through. This is the conditional critical regions. And because if I don't breeze through, we'll kind of fall behind. This is the third week, and according to our schedule, by the way, I'm not going to repeat this all the time. I tend to be in line with the expected number of lectures that I publish in handouts. So we should be at this stage to be beginning with CSP. In your handout, so far what we were doing was fundamentals. I don't have a full-scale, bigger size handout with the small. We're supposed to have spent 4 lectures on it, and we did. We should today begin on distributed algorithms. Which begins CSP. So what I want to do is explain a little bit the CCR and a lot of caveats about it. Yeah?
Before maybe we get started, I have a quick question about this ID, or whatever you want to call it, the paper on, there were some questions on the reviews about possibly
there was a contribution by somebody, I think one sitting in front of you, claiming that his algorithm is incorrect. If you happen to believe that, then say so on the next. If you happen to believe that the argument is faulty, then say so.
I think the only question I really have is that his definition of a weak semaphore.
Yeah. Let me kind of try to contain this kind of discussion by saying that we are not going to have the amount of time this kind of a discussion requires. And that was the reason that I had devised this loose group scheme a year and a half ago, and works well for that kind of purpose. But since there is this question being raised anyway, let me put up. Which one are you talking about here? One of these two?
What is the definition of a weak semaphore? Not the definition of strong.
He doesn't give one, if that's what you're asking.
Well,
He just, well, yeah, but he only mentions the assumption he's making. But go ahead, what's your question?
Well, is it, see, part of the way I'm thinking that he defines a weak semaphore to be one that will not allow, or will only allow, it actually will not allow a process that executes a B to immediately go back around and do a P.
Right.
Okay. Is it also true that
that's this statement.
Okay.
You know, the question is, well, it is much useful to all of us to do a bottom up. Give us the bottom question first. What do you ultimately intend to ask?
Well, I want to ask it. What I want to ask is if there is a process waiting on one P enter and another process waiting on a PQ and a process that finishes the PQ and execute the VM. Okay.
No, it first must do the
Well, it
structure of
does PE, but basically, when it does a VM, there's a process waiting at a
Okay,
PQ.
I'm going to cut the question and say, write the question up and contribute that question
Well,
itself.
it's basically an argument contribution.
For instance, it's possible for a process that is going to do a key operation. It's possible for another process to do some other statements and reach that same semaphore and do a key operation only before the other process that was working. Can you answer the question?
Yeah.
What is the ambiguity in this?
No, according to Newton's algorithm, that's allowed. That's okay.
What is allowed? That is not allowed.
Yeah.
Provided.
Only the last process, the process that executed the last key operation, they're going to do a key operation before the other process. But it doesn't say anything about any other processes.
Says that one of the processes is blocked with a simple passive when B is performed.
Yeah, I mean, I don't see this. The answer to your question is very clearly present in between these two. In fact, this one paragraph is answering it. Look, I mean, I know that this is one of the reasons why I front load these things in the course is these algorithms take a long time to really be understood. There's a lot of what we call the other side of the line profession. There's a lot of sinking time that it requires. And so there's nothing wrong that you're somewhat puzzled about one thing or another at this stage. But to expect them to be resolved in the class with class time, that's not going to be possible in this course. So any doubts you have, put them in as clear a form as possible and post them. And these are so nerve-wracking and mind-boggling kinds of suggestions that you can make that I can't possibly refute them all or agree with them all, even when they're right. So that's where I hope the other students, who by now should be able to also answer the same questions with about the same confidence that I have, so that they can answer them themselves. So that's the overall goal of the news group. But let me, as a general observation, right? And this being a general observation is not always right, not always true. One of the reasons that I said that your term papers should only be based on journal articles is because journal articles go through a process known as refereeing, peer refereeing. That is, if I write a paper and I want that to appear in a technical journal, people of my caliber will read this carefully. And they, first of all, give a technical opinion. Is it technically valid? Is he making any mistakes, etc. Only secondarily do they comment upon the style. That I could have explained it better, my English stinks, etc. That's a secondary. The first order of business that they have, referees have, is it technically valid? And this process, depending on the journal, can take anywhere from a few weeks to 2, 3, 4 years. And in the process, the referee will typically say, well, it almost looks all right, but here is a definition that is somewhat weak. You can reword it, you can make it better, etc. And so it goes through a process known as revision. The author then makes a new version out of the old paper and sends it back, answering all the questions and comments that the referee raises. Now, the end result of all of this is a paper that is published in a journal is probably impeccable, is probably error-free. That's the statement I wanted to tell you about. And I went through this description of what happens and how we do it, just to give you some credibility, to give that statement some credibility in your mind. Because not many of you are familiar with this. What happens when you submit a paper. So, If you're going to immediately criticize either Ewing or somebody else that there is a mistake somewhere, well, it's going to take a little more effort on your part to convince the world that indeed that is so. Because a certain number of competent people have read it carefully. But this does not mean that errors don't escape. I'm sure you as students must have thanked your stars that, the prof missed this. I got 10 points instead of 5. Right? You wouldn't tell anybody about this. Things like that happen in technical literature also. So I'm not at all telling you that Ewing is perfect. There are no errors in Ewing's algorithm. On the other hand, I am telling you that it's unlikely that algorithm has errors. And because of by the same token, if you do discover an error in his algorithm, you can send the correction to that same journal, and it will go through the normal refereeing process. That is, there ought to be 2 or 3 others who will agree with you, and they won't be 730 students. They will be 730 professors elsewhere who will read through this, and if they agree, you will be famous again. The next 730 class, I will talk about Ewing and just refine that. No, I'm not trying to make fun of it, but I'm trying to describe to you what this whole process of refereeing means and what the process's goals are. The refereeing process's goals. Its main goal is to make technically perfect computations. Even if the English is probably bad, the structure of writing is probably bad, etc. Because we as referees, we worry less about that and more about technical validity. So, as I said, we are probably going to run out of time on a number of these topics. And that's one of the reasons I was going to rush through the conditional and critical reason, which is, roughly speaking, the next chapter. Because I want to begin CSP. Now, whenever I have time, I would be happy to start an open discussion like this. But right now, as you saw from my schedule, third week we should have been on distributor algorithms, and halfway through the lecture we are still not even doing CCR. So I don't need to cut this discussion down, but it seems to me that some of those questions can be answered by these paragraphs themselves. Now, one comment I do make, when you make submissions to the news, try to format them as legibly as you can. One big paragraph is hard to read. You need to structure it so that, and the typical structuring that works in all writing is the pyramid structure. Namely, you highlight the point you are trying to establish. You just assert it. And then you substantiate. So that we can get the overall structure of your argument by just looking at the assertions you are making, without necessarily agreeing or disagreeing with it. And after following each assertion, you substantiate. Why do you think that is true? So if you instead throw it as some poorly structured thing, you're going to make our job that much harder. Unfortunately, most of the world has come to the following. People are doing only write-only stuff. It's no longer read-only or read most of the time and write only occasionally. Seems like there are far too many writers and far too few readers. So it is the responsibility of the writer to encourage the reader to read. Okay, the only role reversal occurs in a classroom situation, not elsewhere. Okay. So much for the meta-level discussion, and let's talk quickly about what the so-called conditional critical region This is from your old book, Peterson and Silverschatz, and whoever else is the current co-author. We have written await B arrow S so far. A particular version of this, a particular syntactic triggering of this, is that region R when B do S, and odd is the reversal spelling of 2. Okay? So these are semantically highly related, almost one and the same. But the second one is a syntactically more usable one than the first one. In the first one, we are not telling at all what kinds of shared variables will be used in the B. Whereas in the second form, having said region R, only those things that are part of this so-called shared region R are allowed to be used within B as well as within S. So that if this were a real-life construct in a programming language, the compiler already knows by the time it is looking at B and S, it already knows which shared variables are permitted in there, which ones are not. So that if by mistake you are referring to things that belong to some other shared region, it can complain to you, much like this variable is undeclared kind of messages. Okay? So for that reason, we, in the programming language context, we prefer the second version to the first one. Okay? Now the problem here is, as before, implementing this. So let me summarize these two. The await statement is different from the region statement only in syntax, not in intent, not in meaning. Okay? Now, the goal of this kind of CCR chapter in the book is how do we implement this conditional critical region statement? Implement using what? Well, using semaphores. You are given semaphores. You want conditional critical regions. So if you wish, think of it as the following problem. This region statement happens to be part of a programming language, and you are building a compiler. You know how to generate the code for all the rest of it. You're asking, what code should I produce for this, for the region statement? Are we clear on the problem description? And CCR chapter of your book is talking about that. How do we implement conditional critical regions? Okay? And in the next few minutes, I'm going to flash at you a whole bunch of implementations of this. Some of them are correct, some of them are not. But all of them are coming from well-known places. Okay? Nearly all of them are discussed in the exercises section of the book. So, here we go. This is the first one. This is from the book, Peterson Silverschatz. Depending on how you want to split hairs, this is incorrect. I did show the page number because there are far too many editions of this book. You're not going to be able to take this down, but I'll be happy to loan you my slide. This is in one of the exercises at the end of the chapter. And the author gives the name of this author. The name of this author is Wright. And this also is a version of one of the discussed solutions in that chapter. But as you can see, now it has become quite a bit more complicated. But you will note that this is using passing the baton technique. So if you understood the passing the baton technique in the previous chapter, you will follow this chapter. this one, I'm not going to show you whether it is correct or not. This one I made a note that is on page 261, exercise 530. The code is all in the book. And he asks, is this okay? Is there a problem with it, etc.? The standard bottom line question there is, if it is incorrect, give us a scenario showing that it is incorrect. If it is correct, give us a proof that it is correct. Now, of course, in this class, I would be happy to replace the word prove with convincing and authority. So, and there are a few other similar looking algorithms discussed in that chapter. So I guess the intent of this rushing through is obvious. Intent is this is a reading assignment chapter for CCR. Okay. Now CSP is one topic that is extremely fundamental to distributed computing. And the author spends enough time, but unfortunately he presents a minor variation due to Andrews himself in the book. Whereas I think, because it's such a classic piece of work, you should read the original CSP paper, which is cited in my handout. Okay? And I'm going to be discussing the original paper at some length here. I'm told that in the immediate preceding 434, this was taught, but I'm not sure everybody here has been taught this in the past. How many of you have been through this paper or this material, CSP? Okay, there are about half a dozen, so let's see if we can go past right now. This slide pretty much captures everything about CSP. On the other hand, there are a lot of subtleties in there. So first, let's look at the so-called guarded command. The guarded command, and I'm repeating his naming of this, because this is a very well accepted term now in literature. This is really the statement that we have been using so far. But rather than use the if, phi as the keywords, he uses left bracket and right bracket as the delimiters of each statement. The fat bar that I show there is the same fat bar that we discussed at some length. So, this entire so-called guarded command, or what we call until now simply a statement, is executed as follows. The system, computer that is, evaluates these Boolean expressions. Let's say concurrently. Let us say there. Okay, not required. And it may find one or more of these Boolean expressions to be true. In which case, it can arbitrarily select the corresponding f sub I for those Boolean expressions that evaluated to true. For example, if B2 evaluated to true, it can execute S2. So, from among the many Boolean expressions that are true, the system is entitled to choose any corresponding S, but it will only choose one corresponding S and execute. It is kind of a bad thing for all the Boolean expressions to turn out to false. In other words, none of them is true. So that there is no corresponding S that we could choose. That is a bad thing. And this is a bad thing in the following sense, and we won't further explain this word. Your system quote unquote crashes. The word that the author uses is aborts. So, if at all you doubt if some of these Boolean expressions may turn out to be false, you make sure that some other Boolean expression will turn out to be true at all times. If not, be prepared to accept the whole program to quote unquote abort. Now, a typical way, of course, we write our Boolean guards here would be that B1 probably, let's say there are two prongs in this. And if B1 is the negation of B2, well, then obviously one of them will be true at all times. Remember that our Boolean expressions never have a middle value. They are either true or they are false. There's no maybe or there's no undefined, etc. Okay. So as a result, you may frequently do that. You write guarded statements in such a way that there are two Boolean guards. One is the negation of the other. So the overall general rule is, if you take the ORing of all of these Boolean expressions, B1 or B2 or B3, etc., they are true. If so, then one or more of them is guaranteed at all times to be true. Okay, so much for guarded state. So, but for this subtlety there about abort and about the fat bar, this is what you have seen so far. The corresponding do loop is produced by simply prepending the star in front of the statement. Okay? So right now there is nothing in front of this left bracket. And if I put a star there, this old if statement becomes a do statement. Okay? Whereas if all the Booleans are false, the if statement crashes. If all the Booleans are false, the do statement simply terminates. It doesn't crash. So, whereas it is undesirable to have all the Booleans to be false in an if statement, it is expected that in a do loop, in a do statement, all the Booleans will turn out to be false, hopefully sometime. So all of that is pretty much old material explained in a slightly different way. So what is crucial, what is really new in CSP is this. The so-called input-output represented by the query symbol, the question mark symbol, and the exclamation or the bang symbol. These two represent input-output. And unlike other notations and other languages, these are fundamental in CSP. And it does them in a very peculiar way. For example, if this process named A wishes to output the number 5 to a process named B, we write it like so. So this is an infix binary operator. Left-hand side is the target process. Right-hand side is the expression which is going to be sent. Okay. So in this case, the process whose name is A must name the target, must name the recipient, in this case B. And to this process named B, A is giving the number 5. Okay? And this is known as output. And this we will from now on also call the send operation. Okay? So B bang 5 is a send operation to the process named B. Send what? The value 5. Yeah.
Is there a facility for a single process to have multiple input ports if you want?
Now, right now, this is the end. And in that sense, it's going to appear to you to be extremely primitive, and it is. So, output 5 to B is being done by the process named A. Similarly, the process named B wants to get something from the process named A. But of course, it doesn't know quite what it is going to get. So it provides a receptacle named here as X. So whatever it gets from A is going to be stored in this X here. So if indeed this thing matches with the B bank 5, A is sending 5 to B, and B wants to get something and put it into X. So that after these two have happened, the result of X is, the result that is in X is the number 5. Right? Okay? So, once again, in the case of the process named B, it explicitly names the source. Who is going to give it something? And it also provides a place for it. Later on you'll see that we don't have to do this. We don't have to provide a place for it. We could quite literally say A query 5. What we are saying is, either you give me 5 or else I don't want whatever you give. But we'll come to that meaning a little bit later. So, in this process named B, we name the sender or the source, and we typically name where we are going to receive this stuff in. Okay. Now, the critical thing to remember is that this happens simultaneously. Viewed from within the process named A, it's an event. Viewed from within the process B, it's an event. Viewed from the outside of A and B, we may wonder, are these the same event or not? And now we are giving you the answer. Do not wonder. It's one event. Viewed from outside of A and B, this is one event as in it happened at exactly the same moment. Alright? Of course, A thinks that he sent something, B thinks that he received something. But we, being other than A and B, we just think of this as one I/O event occurred.
So, for instance, process B would block until process A is sent.
Right. So, if A is ready to give the 5 to B, but B is not ready to receive this anywhere, then A is waiting. Because even though it is ready to send, the receiver, in this case B, is not ready to receive. Similarly, B here is ready to receive this number in X from A, but A is doing something else. A is yet to do this output, in which case B is waiting. B is blocked. Okay. So, blocking is pretty fundamental here. And you could easily make a programming mistake and produce a deadlocked bunch of processes. Deadlocked not really because of resource problems, but because of bugs. Okay. So, a couple of non-assumptions. Assumptions that we did not make, just to emphasize. There's no buffering at all in this. Yeah. So A wants to send something to B. A is able to do this exactly when B is able to receive it. And vice versa. B is able to receive it exactly when A is able to send it. Alright. Now, of course, there are quite a few rules beyond this that have to do with effectively syntactic things. And unfortunately, they complicate these ideas, but we need to deal with it. But let me stop here and ask, is this quite clear? Okay. So on top of what we said, we now have these additional things happening to their course. Here is an assignment statement. Later on, we are going to argue that in this language, assignment statement is not a primitive, meaning it can be done using the bang on the query. But for now, we ignore that. So C is a variable in the way that you know it. And C is being assigned a certain value. And this is where the syntax is somewhat unfortunate. This P, empty parentheses, is not your C programming function being invoked with no arguments. It is instead a certain pattern of value. And just as a record of 3 things is a pattern of 3 separate values, in this case, it is a pattern of values. In this case, the value has a specific name, just as the number 5 is a specific name to a certain value. This thing, the P and the empty parentheses, is a specific denotation, a specific way of writing a specific value. Are we clear on that? Just as 5 is a way of writing a certain number that you all know, this represents, the P and the 2 parentheses represents a particular value. And you can kind of guess what value that is. This has to do with our P operating on semaphores. But for now, don't get into that yet. It is some value whose structure, whose pattern, structure as in, the carbon structure is so many this, so many that kind of structure. In that sense, the structure of that value is this P followed by 2 parentheses. And that value is being assigned to C. So this is an assignment statement, very much like I : equals 5. Right? What is surprising is this one. This is similar to writing 5 : equals I. Right? This statement you probably never saw in any language. 5 : equals I. Well, we are introducing that here. This statement, of course, cannot change the value P, whose structure and representation is P and the parentheses. It cannot change it. So it kind of fails when C has a value other than P. It succeeds by doing nothing really when C is containing the value P parentheses. So in other words, by analogy, if you look at the assignment statement 5 : equals I, that statement fails unless the value of I is 5. And when it is 5, it is really not taking the 5 of I and then storing it in the left-hand side. It merely succeeds. But if the value of I is anything other than 5, that statement would have aborted, would have failed. So as you can guess, this is probably the purpose of putting it in there, to forcibly abort it if these two are not equal.
Abort the program or abort the
About the whole thing. Any statement that gets aborted, will abort the process. And we'll worry whether it aborts the entire program or not. The process certainly gets aborted. Okay. And now we can talk about the word match. We can say C matches with P parentheses if the value C can be assigned successfully to P parentheses, as in the second assignment, the crazy assignment. If you're able to do that, and if it doesn't fail, then we can say these two match. And this is the basic, this is the fundamental idea of the match in CHP. And this, once you get this idea clear, we can do fairly sophisticated things with it. For example, this one is actually doing the equivalent of n assigned 2 times x plus 1. And the structure that we placed around it, insert and insert. Again, these are non-functional invocations. Is simply doing this match. And by that reason, this, of course, fails. Because you have insert on the left-hand side, you have has on the right-hand side. So now we can show you how semaphores are implementable in this language. Now, you saw what this language has so far. It has the guarded statements, state statements, the do loops, the fat bars, and it has, of course, the parallel bar, the semicolon, etc. And it has the input-output operations, the bang and the query. That's the language. It does not have built-in semaphores in it. And now we are asking, can this language implement semaphore? And here is a specific answer. The big X is a user process. And there are a whole number of them. And the I there is the identity of that process. Okay. This being a rather low-level, basic kind of language, we are not providing facilities for naming processes in a very sophisticated manner. In this case, this is the ith process in an array of processes called X. Okay. So why this is X, parentheses I, ignore that issue. This process is queried, meaning what? It wants to input the process where this line appears, wants to input from the process named X sub I a certain value. And the value that it wants to input is exactly V parentheses. Are we clear on this? This entire line appears in some process, say A. The process A wishes to do an input operation. How do I know that? The query. The question mark symbol tells me that. What does it want to input? Exactly this one particular structured value, V parentheses. Nothing else. Who does it want to input from? X sub I. So hopefully this X sub I is still there. Okay. We didn't discuss yet what happens if X sub I died meanwhile, or was never born. So let's not assume either one of them. It's there, sitting. So from the ith process, input a value whose structure is this V parentheses. And it will not take any other input. Note that if X sub I outputs something else, such as the number 6, that doesn't cause this process to stop waiting and then abort. It simply doesn't match. If x sub I outputs at 6, that does not cause this process to get out of this waiting. Now, x sub I outputs 6, naming the target, right? Suppose it named this guy A. Now, this guy is not willing to receive anything other than this V, right? So what happens to these two processes? The process A, which has this line, is blocked. The process that tries to do an output of 6 is also blocked. Will either of these ever get out of these waiting? No. So one mismatch, the whole thing comes to grounding, grinding halt. Okay, so that's what that is. Well, what is this one? Well, whichever process that contains that line of code is naming the target process, whose name is send. So this process, again call this process A wants to send something to send. And what does it want to send? It wants to send P, structured value P. Okay? Now I'm showing you the actual structure of the process named send. And this is our typical syntax. The double colon simply says the left-hand side of the double colon is the name for the right-hand side piece of code. So send is the name for all that appears on the right-hand side of the double colon, which is declaring a local variable s integer. You initialize it to whatever you care, non-negative of course. And then onwards, it is in a do loop. Within the do loop, it does one of these two things non-deterministically at all times. If it receives from a process named X a V operation, this is what it will do. And on the other hand, if this guard is true, it will do that. Remember the guard, the Boolean expression? Now let me explain to you the details of that. That guard, the one in red, here, underlined in red, that guard is true provided two things are true. S is greater than 0, followed by receiving a P input value from process named Y. Okay? And this is where a very significant subtlety enters. And it's very hard to explain. Suppose S is greater than 0. Now this is part of this Boolean guard. This CSP does not say the following. Okay, this is what it does not say. It does not say, oh, therefore, having tested this, S is now greater than 0, let's wait for P, getting a P from a Y. It does not say that. Even though it checked and found that S is greater than 0. Okay? So the semicolon semantics of the first lecture is not valid in that context. Are we clear on what it does not say? And I'll tell you what it does say.
Can you say that again? Say again what it does.
Suppose S is 2, right now, magically. So S greater than 0. Tested, true. Well, semicolon or old semicolon does what? Oh, therefore, I can hang around here, right? For however long I want. And why would I hang around? Well, because maybe I haven't gotten the P yet from the guy named Y. Why don't we wait for this P to arrive from the process named Y? This, it is not saying. Even though, if all of us looked at this variable S, it is greater than 0. So is there any administrative reason? On the other hand, okay, again, so now I'm telling you a little bit about what it is saying. Suppose the process named Y is ready to send the P to you, you being the sender. Okay? So, nothing wrong with the process Y. Assumptions are good for us. Y is ready and willing to give you a P, you being the sender. However, the semaphore S is 0 at the moment. Then we won't take it. Why? Our precondition for that action is S greater than 0. Even though Y is ready to give us the P. Okay? So, there is a notion of a guard being enabled. In this case, we say that the red underlined guard, when S is equal to 0, that guard is disabled. It is not enabled. But when a guard is enabled, whether it will become true or not depends on other processes. In this case, Y. A guard is enabled when S is greater than 0, this guard, and it will become true if Y is ready to do a send of P, to send. Clear enough? Yeah, I mean, it takes a while, so please, feel free to.
So what you're saying is that within a guard, this type of operator operates differently than in the main program.
Than in the older style that we were used the semicolon.
No, I wasn't speaking of the semicolon. I was speaking of the
Just the guard?
query operator.
Oh, yes, yes.
So in normal use, it would block there waiting for it.
Waiting for it, right. But remember that this whole thing was preceded by the fat bar. So if you are looking at these two guards, the green and the red one, they are combined with, the entire statement are combined with the fat bar, the non-deterministic bar. Non-determinism implies in this situation here that you are not deliberately pessimistic. You can, depending on what you think might work out, do one or the other. So, the fat bar, even without this S greater than 0, suppose we get rid of that. The fat bar is saying either you take V from X or you take P from Y. Right? In which case, it would be pretty wrong for you being Sam, to commit to taking a P from Y when actually Y was not ready to give it to you. But X was ready to give you a V, but you don't want it.
In the event that neither one was ready to give it up,
Then of course this process is waiting for one of these two things to happen.
and that's like a deadlock. So it'd be
If either X is not, if both X and Y are not ready to output these corresponding values, this process is waiting. If neither X nor Y will ever do these corresponding operations, then we have a completely blocked system. Okay. Are we clear on this? On the point where we do not have S greater than 0. Scratch that part out. Fair enough? Yeah.
So is this really a loop?
This is a loop, yeah, the star. So in other words, it does one of these operations, it accepts one of these inputs, either V input or the P input, does whatever on the right hand side, and is ready to do it again.
Yeah, it makes sense that it's a loop from what it's trying to do, but remembering the loop syntax, if all of your guards evaluate to false, the loop terminates.
Well, right.
But
this one, well, question is, and this is the thing that I so far carefully didn't tell you, when would both of these guards be false? Suppose I have X query V, Y query P, no S greater than 0 stuff. Well, they're not false. Not yet. When will they be false? Well, suppose X dies magically. Then there is no hope of this being true, right? So that part is false. Now we are left with one guard. Y greater than Y query P. If Y also dies, now that also is false. So in other words, if you look at an if statement or a do statement, and if you have guarded statements that include the query, the corresponding query guard will be false if the source that is named terminated.
what will be true otherwise?
Well, no. Will hopefully be true in the sense of liveness sometime into the future.
Right. But if you take in some moment,
Unless you can prove that that process will never send you this value.
if at some moment in time X is not ready to send V and Y is not ready to send P,
Then you wait.
okay,
And
so
neither of them are true.
right, and getting back to my original question, then this isn't exactly like a standard loop either.
No, then they are kind of waiting for something to happen. Then this end is waiting for something to happen.
Okay.
Until then, none of these increment-decrement things will occur.
So in general, a loop that has guards that aren't queries will terminate when all of its queries return false.
Right.
A loop that has guards that are queries.
I'm in here, start all over. This last part.
A loop that has guards that are not queries will terminate when all those guards
Okay,
evaluate
so
false.
something like this. B1, B2, no queries in them.
Right, no queries.
Okay.
If B1 and B2 both evaluate to false.
Then that terminates.
Right, now, let's say that B1 and B2 are both queries.
Okay. So now we are looking at another example where this is an input from A into X, this is an input from B into Y, and add bar. This terminates only when A and B did.
A and B?
A died. If A simply died, this is gone. If B also died, this is also gone.
Okay, so
In which case we are terminated.
now I don't know if this case would ever come up, but let's say that B1 is a query and B2 is not.
Well, in which case the same rule. So now we are back to B1. It will come up, in fact. B1 is a normal Boolean expression and some statement. And now let's use A here. A query X and some other statement. Suppose at this moment B1 is false. So that's gone. That guard that B1 and S1 cannot use. Now if A is alive, but not ready to give us an X, well, we're going to be waiting on that. It's not true yet, nor is it false.
There will be not any condition except that the process dies that it will become false.
Right now there are no other conditions when this will become false. A query X. But you know from our previous rules, if A sends you something that doesn't match with the structure of X, this is a fail altogether. This is a deadlock. Okay. But when we are trying to understand the central line semantics of this notation, let's not worry about this crazy situation. Let's still go with the mainline core meaning of this. Okay, now we are going to be claiming the following. This sem, suggestively named, is the semaphore. So far, we thought of sem as a semaphores, as a passive data type. Now it has become an active process by itself. Of course, x and y are arbitrary processes, not the specific x and the specific y. Whoever wants to use this semaphore. Okay. Right now, believe that there is some way of using x wherever necessary. Similarly, y. So imagine that somehow we are able to say x and y in that piece of code stand for arbitrary processes, excepting, of course, sem itself. Right? That doesn't make sense. If it tries to send something to itself, you're immediately blocked. Right? Right? No? This doesn't make sense to do that. Because it cannot both be sending and receiving at the same time. Okay? In a similar way,
Do you have a parallel bar construct here?
there is a parallel bar construct. But even so, it is a very tough thing to deal with this. So we will never ever do self-sending. There is a parallel bar construct. So, with the proviso that x and y stand for arbitrary process names, you should be able to see that this is a general semaphore, that is a counting semaphore, right? It's not just a binary semaphore. Depending on how you use it, it could be binary, but it also can be used, this thing can be used as a general counting semaphore. Now, what kind of a semaphore is this? As in weak, very weak, strong, not so strong, etc.
Very weak.
What do you think? What are the details of who can do a P operation following a V, etc.? I've given you all the rules to answer that question so far.
Can X and Y be the same process?
The question is, can X and Y be the same process? In terms of the syntax, yes.
Okay.
But, so in terms of this process, sem is concerned, there's nothing wrong with that. But in terms of the other process, the X or the Y, now that they are the same, that process could not both be doing send a V as well as send a P. It's doing one of two. Or maybe something else.
Seems like it would be possible for it to do a V and then P and anything afterwards. But it seems like
Yeah.
anything
Right.
preventing it from doing that.
So the question was, the way we are trying to resolve this, weak versus strong semaphore is, suppose a certain process did a V. Could it or could it not do a V operation right away, even though there are other processes which were trying to send a P? So far, we didn't say anything. If this Y could somehow be used for an arbitrary process name, kind of like the regular expression version of whatever matches, like a while pattern there. If all of those processes are trying to do a P operation. All that matters to us is that this query operation mate with exactly one of them. Which one it mates, no further details are given. So this is a very weak semaphore. On the other hand, are we going to be in a bad shape in terms of the value of S? That is, we got a V operation, we were yet to do the increment. Meanwhile, could we accept a P and decrement it?
No, because this process won't be ready to.
Right? This process won't be ready until after it has incremented the S. So there is that delay present between the V and the succeeding P operation. Okay? So, what does this prove? Well, it proves that this particular language is as powerful as semaphores. Therefore, whatever you can solve using semaphores, you can solve using this. Right? Now, let us do a simple exercise. And the more complicated version of this exercise, you need to read at home. Otherwise, we won't be able to finish it here. Next class. This is implementing a data structure that you can think of as a set of numbers. This data structure. And this data structure need not grow to arbitrary size. And so we are modestly calling this a small set. In particular, our set is not going to contain more than 100 numbers total. So following our CS240 kind of techniques, we are implementing the set as an array of numbers, and this counter size will tell us how many of these array items are filled at any moment. Okay. And beyond that, there are unfilled array elements. Okay, so we are using an array in the obvious way to represent a set of numbers, which we are going to be sure that will not exceed 100. Okay? And we are writing the code for this data structure. Now, in this language, these things will not anymore be passive things in this language, in CSP. In CSP, things that are normally passive become processes, active things. For example, you just saw semaphore become a process. So in this case, this small set of integers is going to be a process. It's what we now call a server. This small set of integers is a server. And it has a bunch of clients. What will these clients ask the server to do? They will ask, could you please store this number in your set? They will ask, have you got this number in your set? They will ask, delete this number if you have it. Okay? So these are the kinds of requests that the client will make on the server. In this piece of code here, I'm only showing you two requests. Have you got it? Or insert this number. The delete is not shown in this. Okay? So have you got this number n is queried like so. So this process is willing to receive this patterned value has n. From who? From a client process X. Having received that, it will do this piece of code called search. Search is shown below. Having done search, what does it do? It outputs to this client X the Boolean value. If I is less than size, we count it. If I is greater than or equal to size, we did it. Okay? Because the client is simply asking, have you got this number in your set? Similarly, the client asks us to insert a number n into our set. And this being a set, since already kind of small, we don't want to store duplicate items. So we do a search. If it's already there, we don't really complain, just do nothing. But if it is not already there, then we increment the size and we store the number. Okay, that's all this is doing. Fair enough? So you need, on this slide, the only thing that is new is the notation. Any 240 student should be able to do this. Right? Now, what is the drawback for us so far as 730 is concerned? Well, it's using just one process. And this one process does only one thing at a time. While it is inserting, it will not answer anybody asking questions about has. And while it is doing the has question, it won't take requests for inserting. Right? It does one thing at a time, as you can see. Having received one of these requests, it does the right-hand side of the arrows. And right-hand side of the arrow itself includes a fairly compute-intensive loop, depending on the size. And while it's doing that, we won't accept any more inputs. So, we want to do this using a number of processes, not just one. And in order to make you use more than really realistic number of processes, we insist the following. Okay, this is just to make the problem interesting. Use as many processes as there are items in the array. So in this case, we have 100 items. So now we are saying use 100 processes. Not very realistic, but to get an understanding of this notation, do it. So each process either has exactly one number or none. Just like these array elements are either filled or they are vacant. Now in order to speed up the search, you want to order the array in this particular way. Like to write increasing order. No duplicate items. Okay. And that is the one that is discussed in the paper in the next section following this one. We do that. That's a fairly subtle algorithm.